Hello, welcome back to this lesson in engineering circuit analysis. We're studying op amps, and we're studying the concept of the difference amplifier circuit, which we have drawn a basic idea of on the board. This lesson is a theory lesson. What I'm going to do is explain to you the concept of what a difference amplifier is, and we're going to do the mathematics in order to derive what the gain equation basically is for this circuit that's on the board. Now, I want to caution you ahead of time that when you watch any of these derivation lessons, I don't expect any of you to really have the end game in your head or to be able to map out a path to the answer in your head beforehand. I mean, nobody understands this stuff until you see it the first time. So when you go through this derivation with me, don't beat yourself up if you're not saying, well, gee, I never would have saw that, or I never would have been able to figure that out. Well, a lot of things are like that in math and science. So you don't really necessarily can see the answer until you see it done once. But what you should be able to do is follow with me step by step logically, so that when we finally do get to the answer, you will know where that equation came from and all of the assumptions that drove it, and so that you can mathematically could reproduce it yourself. At the end of the day, we want to figure out what the output here of this amplifier is, and we're trying to get an output equation relative to the difference of the inputs. You see, this is the one of the first times we've actually seen, we may have had something like this in the basic op-amp discussion, but basically in this case what we're trying to do is we're not trying to amplify A by itself or B by itself. What we're trying to do is take the difference, the subtraction of these two things, and then we want to get what that difference is, and then we want to amplify that. Right? So that's what this is going to do. And this has applications in all kinds of things. Maybe you have a signal coming from reactor A in a nuclear power plant, and you have a signal coming from reactor B in a different part of the nuclear power plant. They should be running the same and generating the same power, right? So you take those two signals in, and you want to know what the difference is between them. You want to know if they're differing from each other. You want to know what the power output difference is. So you subtract them and you amplify it. So this is a signal could be coming from power plant A, power plant B, and you're going to do some magic here. We're going to figure it all out and get the math down so that you could subtract these signals, amplify it, and then send the output to a computer or some other monitoring device. That's just one example, but you get the idea. All right, so this is going to proceed as follows. We're going to write some equations down that you know to be true, and we're going to basically beat them into shape so that we can get an output equation as a function of the difference of the inputs. That's why this is called a difference amplifier. So what we really want to do at the end of the day is I want you to keep this in the back of your head because you need to know where we're going, right? We want V out, right, to be proportional, that's what this alpha means, lowercase alpha, to VB minus VA. So this proportionality is not an equal sign because we don't know what scaling coefficient is going to be in front of here, but basically at the end of the day you're going to get the output is equal to some scaling number, which is going to be the resistors, multiplied by the difference. You see the difference is here. So the proportionality means that that's going to be governed by the gain equation that we get. But this is the form of the output that we want to get. All right, so we have to start somewhere. When you do this kind of derivation, what you really should do is say, I know where I want to go. I don't know how to get there yet, but what I'm going to do is write down all of the valid equations that I know are true, right? And then see if I can combine those equations somehow to get the form of the output that I'm actually looking for. So I don't know how to get to the answer yet. I don't know that ahead of time, but I know where I want to go, and I write down everything that I can write down. So I know, for instance, if I write a node voltage equation right here, it's going to be valid. It may not help me, but I know it's going to be valid because node voltage equations are always valid. I also can write a node voltage equation here at this node. That will always be valid as well. So that's about as far as I've gotten, mentally here, but that's what I'm going to do. Let's write a node voltage here. Let's write a node voltage here. Let's write whatever constraints we can down, and then let's look at them and see if we can combine them in such a way to get this. And that's how we're going to handle it. So let's first do a node voltage at the inverting input, which is this one up here, right? So we know that a node voltage is basically Kirchhoff's law in disguise. You're summing the current through this leg, through this leg, through this leg, and they have to sum equal to 0. So when you look at the current going through this leg, what we first need to realize is that these two points, these two nodes, which are connected to the inputs of the amplifier, they basically track each other because of the virtual short condition. And we've been labeling the voltage at this non-inverting terminal, we've been calling it V sub 2 for the whole course, and we've been calling this one V sub 1 for the whole course. And we're going to write it down later, but we know that V2 is got to be equal to V1 for the ideal amplifier case. So what we're going to do is write